Humans possess a built-in mechanism for self-correction. We can stop mid-thought, realize our logic is flawed, and change course before we commit to an answer. Early language models lacked this internal friction. They possessed access to billions of parameters of human knowledge, but they possessed no instinct to doubt their own conclusions. To give models access to external facts, engineers built Retrieval Augmented Generation, or RAG. In this system, the model receives a prompt, searches a database to retrieve relevant documents, and generates an answer. But if retrieved information is incorrect, the model does not pause. The pipeline pushes weak evidence straight through to the final output. This architecture creates a severe vulnerability: highly articulate systems delivering confident responses built entirely on bad information. The machine simply didn't know what it didn't know. As long as the system cannot pause to verify its own evidence, its reasoning remains fragile. To solve the hallucination problem, researchers began studying how human investigators navigate uncertainty. When a human researcher finds that their evidence is thin, they naturally slow down. They evaluate the credibility of the source and search for additional data to fill the gaps. Engineers translated this investigative loop into code by creating self-RAG, a framework that forces the AI to check its own work against the source material. In this system, the AI evaluates its own reasoning and determines internally if it needs more facts before it generates a final response. This approach transforms retrieval into an adaptive process, where the model itself determines when and how to search for more data based on its own confidence levels. This relies on a reflection layer above the primary text generation path, acting as internal quality control. It uses reflection tokens to intercept data, forcing the system to ask, is this supported, or am I missing context? Consider a query like, what caused the decline of company X? On its first pass, the search engine pulls up reports showing a steep drop in revenue and product failures, but it misses the recent wave of CEO resignations. A classic RAG system would summarize the revenue data and stop, but in a self-RAG architecture, the reflection tokens flag the drafted answer as insufficient. This internal alert triggers a second targeted search. The AI finds the missing executive turnover data and integrates it into a complete narrative. The final answer is more accurate because the system identifies the gaps in its own evidence and fixes them. These self-evaluations work. When reflection is active, the hallucination rate drops significantly while factual accuracy rises. However, this thoughtfulness requires significant resources. Every cycle of critique and secondary searching consumes extra processing power, increases latency, and raises costs. This creates an absurdity with simple queries. If you ask the AI, what is 2 plus 2? The model might still trigger its reflection loops, questioning its own basic math, and wasting compute on a fact that requires no external search. By teaching the AI to scrutinize every prompt with the same intensity, engineers built a system that is accurate but highly inefficient. Solving this efficiency paradox required a final shift in retrieval logic. Instead of only asking, should I retrieve more, the system must first determine, do I need to retrieve anything at all? This leads to the most recent evolution, adaptive RAG. Adaptive RAG acts as a router. Simple, factual queries bypass the database and go straight to the final output. Only complex or nuanced questions are routed into the resource-intensive reflection and search loop. This sorting mechanism lowers compute costs and delivers faster responses, while preserving the accuracy of deep-thinking models. True computational intelligence requires a balance: the depth to double-check complex claims and the speed to process simple facts without hesitation.